Okay, so we've got a particle here, elastic strain, particle weights, so the force on here, that's 48. Don't forget that is actually mg if I need to know what the mass is. And I've got tension, which is, it's giving me lambda, so lambda x over L, and we know that lambda equals 30, L equals 0.6, and its pulled natural length is 0.6, and it's pulled down a whole bit, the whole bit has gone down to there, is d. And I've got to work out, find what that d is, because when it's pulled down and released from there, it just gets there, so it's going to be energy. So I'm going to have total initial energy equals total final energy. And this energy is going to be made up of potential energy, I suppose gravitational potential energy, kinetic energy, and elastic potential energy. Formulas: mgh, half mv squared, and lambda x squared over 2l. That's my formulas. So I'm going to start off by saying that this bit is my baseline, so I'll have nothing there, plus kinetic energy is released from rest, plus lambda, so is 30, times by x squared, and that's the extension, and so natural length 0.6, pulled down d, so that would be d minus 0.6 all over 2l, so 2 times 0.6, and that equals the final energy. It's gone up to here. I'll have no elastic potential energy, I'll have no kinetic energy because it just reaches there, so it's just going to have mgh, and that will be mg is 48, so it's 48 and times the height, which is d, and that's multiply both sides by 1.2, divide by 30, that will give us, oh, I forgot the squared, lambda x squared, and that's why I write it down there, messed up there, not too bad. So we've got d minus 0.6 squared equals 1.92d, so I've got d squared minus 1.2d plus 0.36 equals 1.92d, and so I get d squared equal d squared minus 3.12d plus 0.36 equals 0, and I'll put that into the formula, so d equals minus that, so it's 3.12 plus or minus square root of 3.12 squared, etc., all over 2a, and so d equals 3 or 0.12. Obviously that's rubbish at 0.12 because it was released when d was 0.12, it just dropped down, so it can't be there, so the answer is d must equal 3. And then I'll do this bit in red, so we've got find out magnitude and direction of the acceleration when it's travelled 1.3. So the whole thing down there is 3 meters. It's made up of its natural length, which is 0.6. It's gone up 1.3, and so therefore the middle bit here is 1.9, that's 1.1 meters. And this is what it looks like. I'll put the forces again in G. The weight on the end is 48. This is tension, which equals lambda x over L. And we want to see if t is bigger than 48, the acceleration will be upwards. If it's less than 48, the acceleration will be downwards. So when x equals extension is 1.1, t equals 30 times 1.1 all over 0.6, which equals 55 newtons, which is greater than 48 newtons. Therefore, acceleration is upwards. And now we can work out what it is. We're going to resolve upwards. I'm going to put it on upwards here. I could have done this result anyhow and just worked it out, but there's nothing wrong with doing it like this. Resultant force is mass times acceleration. So what force we've got going upwards? We've got 55 minus the 48 equals the mass, that's mg. So the mass, mg is 48, so mass equals 48 over 9.8 times by the acceleration. So A equals 7 times by 9.8 over 48, which equals 1.429166666, and or which equals 1.43 meters per second squared to 3 significant figures. And that's question 2 done.